First question is obviously quite knowledge based. It's looking at the principal structures, the key structures of the ventilatory system. Yes, some of you found it difficult to identify where this line was going, but if it had been pointing to one of these things here or to one of these things, that would be the bronchioles, and it's not even on the list. So the bronchi are the big ones. The trachea is the pipe, and the larynx is up here. So it has to be the alveoli. Next question, number 2, an athlete is exercising outside. What's the role of the nose? A few of you got this one wrong. So you could think about it's warm, but what is the principal function of the nose? And it's to actually filter. That's why we've got nasal hairs. We filter dust particles out. The mouth and the nose do help to warm the air because the body temperature inside is warmer than the outside air. It does help to warm it, but in this particular question, that's not really a response, so we're thinking about filtration. Question 3. So this is a challenging one, but if we look at the axes, we can think about increased lung volume. So going from deep breathing, which is up here, to shallow breathing, which is our tidal volume. So if we're thinking about a normal breath in and out, like we did in class, tidal volume, our maximal breath in would be B. Our maximal breath out would be coming down, this extra bit here, and obviously our residual volume's down here. So if we add it all together, our total lung volume is going to be our vital capacity, minus the residual volume, which is this bit here. So total lung capacity includes residual volume, but in this instance, we've got our vital capacity, big breath in, big breath out, plus the normal bit in between. Question 4, this threw some of you, so we need to have a look at this diagram I'm going to show you on the right. But when we think about breathing, how do we know whether we need to breathe bigger and heavier? And it's to do with carbon dioxide levels. So most of you remembered that if we've got high CO2, we've got increased acidity. But you were thrown off by the fact that this wasn't on the list. So what do we mean by acidity? We know that carbon dioxide goes up, so it can't be this one or this one. This is to do with O2. So we know it's one of these ones. If I just show you this table quickly, this is about pH. So whether a substance is alkali or acidic, you can see that the number on the litmus scale will go up to 14, i.e. high pH. If it's alkali. If it's acidic, it's actually low pH. So that's a pretty tough question. You can see here things inside the body like stomach acid or CO2, lactic acid building up in the muscles. Those are all examples of acidic things. Urine and water are more neutral. Seawater, for example, is quite salty, so we're becoming more alkaline there. But yeah, low pH. Okay, next one. Okay, we've got the different nodes. I've highlighted them for you. So SA node, AV node, bundle of His, Purkinje fibres. A nice little diagram, very clear. An electrical signal leaves the SA node. So it's this one here, we need to know that. What does that do first? What's the thing it's going to do? Well, let's do process for elimination. It's nothing to do with the ventricles because it's nowhere near them. The ventricles are down here. The atria are up here. So nothing to do with this one. It could be this one, it could be this one. Ventricular contraction we're also going to get rid of. Atrial relaxation, an electrical impulse doesn't relax anything. An electrical signal causes an increase in pressure and therefore contraction. So even if you weren't 100% sure, electricity gives us contraction. Okay, number 6. This is a hard one. Which of the structures of the cardiovascular system are described correctly? So we need to know about oxygenated blood. In fact, let's go oxygenated blood, and we need to know about deoxygenated blood. This is about knowing the structure of the heart. And again, you need to think about the blue side and the red side. So we've got the left side of the heart is all of this stuff. The right side is all of this stuff. So even if you know that one thing, it'll start to let us get rid of some of these options. There's no way that deoxygenated blood is in the left atrium. That's the red side, so we get rid of B. It could be this one, but actually the pulmonary artery is wrong. This one's wrong. It's going to be pulmonary artery is deoxygenated. So yeah, you can do a little bit of process of elimination here, but if we zoom in, oxygenated is the left side of the heart, and the inferior vena cava, or any part of the vena cava, this one or this one, carries deoxygenated blood. So left ventricle oxygenated, and the vena cava, blood coming into the heart, deoxygenated. Number 7, you did very well on. We remembered this idea that static exercises have a really weird response on our arteries. So if you imagine all these muscles here contracting, they're not contracting and relaxing, These muscles, even your glutes to a degree, but all of your muscles are in constant contraction. So because of that, they put in pressure on the surrounding capillaries and blood vessels, which means that there's no relaxation. It's narrowing the vessels from wide to thin, which increases pressure because the same amount of blood is still trying to get through. Even if you weren't sure with that question, you could have probably had a guess at the idea that all of them have movement and this one is still. So it's the odd one out. Sometimes it's useful looking at questions like that. All right, question 8. This threw a lot of you because we haven't done that many database questions in a formal sense, but we're going to have to do more in year 13 and there will be some in the year 12 end of year exam. So let's have a look. First of all, read the blurb. The blurb is there to tell you what is going on in the graph. So let's have a look at the question. It's basically to do with people's VO2 maxes in different conditions. So we've got a control group who, just do a control trial and then they've got a low oxygen condition. But we've also got this IMT group and they have this condition applied where they're doing, inspiratory muscle training up here. So they've got an experimental condition and we're seeing what this changes in comparison to this change. Is there any difference? Does it have much of an impact? Well, let's find out. The first question is just interpreting the data. It's a state question. You don't have to explain anything, but let's have a look. It's IMT and low oxygen. So here's IMT, here's low oxygen, and then we're looking at post-cycling as well, this one here. So physically highlight it. Lots of you knew that it was this one, but you were misreading the graph. So let's draw the line across. You could do this with a pencil if you want to. And it comes at this point here. So some of you put 50. It's not 50. That's this line here, which will be down there. This is 50 to 60. And we've got 1, 2, 3, 4, 5 tick marks or tick lines. So if we divide 10, which is the difference, by 5, that tells us that each little line is worth 2. And therefore, this is 52. All right, next one, tricky. Using the data, deduce the effects of training on VO2 max. So the first thing is, they don't want you to explain anything. They want you to deduce. That means use the graph and say what you see. It's almost like an analyze. What do you see on the graph? But deduce means make sense of. Make sense or draw a conclusion. Conclude. Don't explain it, just draw out information. Because it says training on VO2 max, that means you can say absolutely anything about the graph in front of you. You can say, basically, what is the post result? What do we see happening? Well, the black lines, for a start, and a lot of you got this right, the black lines in every single condition are higher than the white lines. That implies that every time we measure VO2 max after something, that VO2 max has actually increased. What some of you, nobody got this one, but what you might be able to see as well, and a lot of you ignored it, is that this point down here tells us not only did that happen, but pre-cycling has a p-value of less than 0.05. And we know if a p-value is smaller than 0.05, the results are significantly different. So it's statistically proven that there is a difference post result with VO2 max increase. The other thing you could have said is that, we've got this control group here. we've got a control group. They didn't do any weird breathing exercises, but their VO2 max still increased, and it's not actually that much lower than this one. So you could say that the results are quite similar. Check the mark scheme for that one, have a little look, but you're basically saying what you see. That's what we take away from that question.